All right, welcome to 6.3 integration by parts. So this is another new integration method here, and it's just going to be best to do a lot of examples here. So we're going to be looking at the product rule in integral form. So kind of the same idea here, and something called tabular integration, using a table basically. All right, so let's look first at integration by parts. So first of all, it's a way to integrate a challenging integral. The substitution won't work. And you'll see an example here in just a second. But this right here is the formula that we're going to be using. So if we could write the integral as the integral of u dv, notice the non-common variables, then we're going to set it up as uv minus the integral of v du. And what ends up being is taking this complex integral, and it should simplify down to a much simpler integral that we can solve. So here's a quick example. We have x cosine x dx. Well, substitution's not going to work here because the derivative of x is 1, not x. The derivative of cosine is sine. There's no sine. So there's no way to use substitution in this particular problem. So what we want to do here is we want to figure out u and dv from this particular problem. And there is a way to kind of figure out what you want to do here, and that's on the next page. But for right now, this particular problem, we're going to kind of just do by following me here. So we're going to let u be the function x, which means, so this is u, which means the rest of it is dv. So dv is going to be cosine x dx. So let's kind of figure that out. Well, up here on this formula, I have a u and a dv. But the rest of the formula, I need a v. I don't have v. And I need a du. So that means I got to find the derivative of u. Well, the derivative of u with respect to x is x. Or sorry, not x. My fault. Is 1 dx. And the antiderivative of dv, so what was the function to begin with, was sine x. Because the derivative of sine x is cosine x dx. With these pieces of information, I can now take this integral and I can split it by parts, hence the word, it can split it into parts, u times v. So I get x times the sine of x minus the integral of v, which is sine x, du, which was just 1. Oh, that's nice, because look how easy this integral is now. So as an answer, I would get x sine x minus the integral of sine of x is negative cosine. So this negative actually ends up becoming a positive plus c. And you can verify for this for yourself by finding the derivative of this problem. Here you would need the product rule, hence the idea of the product rule from before. You would need the product rule, and then you'd get the derivative of this. Well, guess what? You would end up with a sign and a minus sign, which would go away, which you will get this as its derivative, x cosine x. So this is pretty cool. It's a very simplistic formula. The problem is, just as with substitution, where substitution you had to figure out what u, the variable u was, or the substitution u was, here you have to figure out what should I use for u. And we're going to use this little acronym because it's something I've seen before, and the textbook here kind of mentions it down in the little corner of the textbook. So how do you know what to use for the function u? A common practice here is the anagram, or not anagram? Yeah, whatever it is. Lipit. L is natural logarithm. So this is kind of an order of which you would try to look for. So if you can use the natural logarithm, use it first. If you don't see a natural logarithm and you see a inverse trig function, use it. Then you could just keep going. P would be polynomial, E is exponential, and T is a trigonometric function. So you notice on that first example that we did, I chose the polynomial over the trigonometric function because polynomial came first before trigonometric. And obviously, the more practice you get, the better you'll get at this. So here's two examples. And if you look at the limit here, for this first problem, it's x squared e to the x. Well, x squared is a polynomial, and e to the x is exponential. So I probably want to start with the polynomial. So let's say u is x squared, and therefore du is 2x dx. And that would mean dv is e to the x. And, oops, not d. Then v is e to the x. Oops, sorry, e to the x dx over here. Okay, so I set up my integration by parts. I get u times v, so I get x squared e to the x minus the integral of v du. So 2x e to the x, so my 2 can come out here, x e to the x dx. Now here's a problem. I didn't really choose a lot of easy problems here because you might as well just do the hard ones. So I've set this up, but now I've got x e to the x. But x e to the x, also I can't use substitution, so I have to use by parts again. Well, that's okay. Now we're just practicing the skill twice in the same problem. So let's change it to a red pen here. We're going to u is, now remember we're looking at this thing right here. U is an x, and dv is e to the x dx. Du is 1 dx, is actually kind of where we want to go. And v is e to the x. Which means now we have this piece from before. So we have x squared e to the x minus 2 times. Now I have to split this integral up. So this integral is going to be uv minus the integral of v du. Well, now this is easier solved. Okay, so last final step here would be, okay, so I've got x squared e to the x minus 2x e to the x. And then you got a minus times a minus. That makes a plus 2 times the antiderivative of e to the x, which is e to the x, plus c. And there's your final answer. And if you took the derivative of this nice ugly thing, you will get this nice, pretty simplistic thing, actually. Oh, fun, right? I know you guys are all thinking this is super fun. All right, so I'm going to delete that so I can get to the second problem here. X natural log of x dx. And before we're fully complete, I'm also doing an initial value, which means the initial value is going to have an actual answer, no c value. You're going to get an actual number here. Okay, so in that lipit, the L stands for natural log. So natural log becomes before polynomial. So I'm going to say u is equal to the natural log of x, and therefore dv is x dx. The derivative of u is going to be 1 over x dx. And the integral, or the antiderivative of dv is x squared over 2. No dx, I keep writing that. So let's set this up. Hopefully we don't have to do this twice. Let's set this one up. So u times v. So x squared over 2 times the natural log of x minus the integral of v du. So x squared over 2 times 1 over x dx minus. Okay, whoa, that's nice. X squared over x becomes x. So I'm going to bring out this 1/2, and x squared over x just becomes x. Well, that's so easy. So I get x squared over 2 times the natural log of x minus, well, x, the antiderivative of x is x squared over 2, so I get x squared over 2 times 2, because that 2 is in the denominator there, plus c. And you got to remember that this is equal to y. This is actually our function. But the question is now, let's solve for c, so this being an initial value problem. So y is -1 when x is 1. So 1 over 2, natural log of 1 minus 1 over 4 plus c. Natural log of 1 is just 0. So that becomes 0 minus 1/4 plus c. If you add 1/4 to -1, you get -3/4. So you would take this number and substitute into that. See, not too bad at all. Easy. You just got to figure out what is u and what was dv to begin with. But again, this is going to be one of our 2-day lessons because this is one of those skills that just needs to be kind of mastered. Okay, this one's kind of an interesting one. If you were to look at Lipet, e exponential comes before trigonometric, so that means I'm going to go u is equal to e to the x, and dv is cosine x dx. So derivative of u is e to the x. And the original function was sine x. Okay, this is fun. uv, so e to the x, sine of x minus the integral of e to the x and sine of x. Oh, that doesn't look any simpler. Dang. Let's try this again. Maybe we got to do it twice. Okay, so I'm going to do this again. So u is equal to e to the x. dv is equal to sine of x dx. So du is e to the x dx. And v was negative cosine x. Okay, so let's try that. Let's go there. This means this is now e to the x sine of x, which was to begin with, right? That was the beginning part, minus uv. So now I'm splitting up this integral by parts. So e to the x and times negative cosine of x minus the integral of e to the x sine of x dx. Oops, sorry, not sine of x. My fault. V du. So, and a negative cosine x dx. That doesn't look any simpler either. But let's see. Let's kind of simplify this, get rid of some of those brackets, something like this. So we got e to the x, sine of x, minus and a minus become plus. So plus e to the x cosine of x. This minus comes out. This minus goes with this minus, makes it a plus. That minus makes it a minus. So I get minus e to the x cosine x dx. Now, some of you are probably realizing that if I just keep doing this, I'm just going to go around in circles. And you notice that this e to the x cosine x is actually what we started with. But that's actually where I want to go. Notice that this is an equality. This is an equation. And I have e to the x cosine x dx is equal to this thing. But notice I have this same thing on the right-hand side. So what I can do is I can add this to both sides. Huh, why did I do that? Okay. Anyway, I can add this integral to both sides, and I get 2. Bear with me if you're not following this. E to the x sine x plus e to the x cosine x. But what's actually kind of interesting here is the original question is solve for this, which means I can't have any integrals in my answer. Well, notice this. I have this times 2, which means I can divide both sides by 2. So I get e to the x sine x plus e to the x cosine x over 2. Notice I get no more integrals. Don't forget your plus c. I always forget plus c. Don't forget plus c, because that's going to make a big difference on your AP exams. So this is actually kind of cool, because that's going to be my answer. E to the x sine of x plus e to the x cosine of x all over 2. All right. Last kind of piece here is what we call tabular integration. What this ends up being is something like that particular problem, or actually a problem a couple pages ago where we had to do it twice. Sometimes this integration by parts just gets very repetitious and very annoying, especially if you have to do it more than twice. Twice wasn't so bad. If you had to do that a third time, and a fourth time, a fifth time, that sort of idea. So if you have the integral of f of x times g of x dx, and one of those two functions is easily differentiable all the way down to 0, and the other one is easily integratable, integrated repeatedly. So like e to the x is easily integrated, right? You can integrate it. It's e to the x, e to the x, e to the x, e to the x. Or a trig function like sine, you can integrate it, become cosine, integrate that, become sine again, and that sort of idea. Whereas like f of x might be a good polynomial, something you can integrate all the way down to 0. So here would be an example. This is a shorthand method for integration by parts. So we're going to say that f of x is x squared, and we're going to say g of x is e to the x. Now what we're going to do is just going to create a table. Sorry about that. So g of x is, or sorry, f of x is x squared, g of x is e to the x. Okay, so this table for f of x, so notice this, I'm saying differentiable. So I'm going to find the derivatives. 2x, 2, 0. E to the x, or sorry, e to the x, g of x, I'm going to take the integral. I get e to the x, e to the x, e to the x. And then what we're going to do is we're going to pair up along this diagonal. And we're going to get plus, minus, plus. This is the pattern that you follow. Plus, minus, plus, minus, plus, minus, plus, minus, all the way down. And here's what's super, super cool. Your answer is x squared e to the x minus 2x e to the x plus 2e to the x plus c. And guess what? You didn't have to do any integration by parts. You could use a tabular integration. So nice, so easy. And you could continue this forever. Maybe you started with x to the 6th power. Eventually you get down to 0. It just takes a lot longer. The other one that I had here was x cubed and sine of x. If I just go down this process in my tabular version, I get 3x squared, 6x, 6, and 0. Sine x, cosine x, or sorry, negative cosine x, because we're taking the integral on the other side. Negative sine of x, cosine of x, sine of x. And then we just pair these up. That's a plus, That's a minus. That's a plus. That's a minus. The answer here would be long, but not terribly hard. Negative, because it's a minus cosine. So negative x cubed cosine x. Minus minus makes plus, so 3x squared sine x. Positive positive makes plus 6x cosine x, and a minus 6 sine x plus c. Long, but so fast. All right. I'm going to take these ones for a later date, and I'm going to leave you guys with those ones for now.